Hello everyone. Just for anyone who wants to ask questions, there's a Q&A section, and so it's like on the bottom right. There's a meeting tools button. Just click on it, and then there's like Q&A. You can just ask your questions. And so Juno Nam is going to present today. So I'll just let you introduce yourself and present the topic.
Okay. Yeah, thank you for invite, and thank you everyone for joining. And I'm Juno, and I'm a PhD candidate in MIT Materials Science and Engineering. And today I'll be going to introduce my recent work on enhancing diffusion-based sampling with molecular collective variables. This was my internship project at Meta Ferrochemistry team. And so to briefly introduce what's my work. So this work is concerned about the energy-based training of diffusion samplers. So when we basically try to train the energy-based sampler using the energy function, then we might get locked in a certain mode, and we try to evade that problem using another adaptive bias that is stacked on the low-dimensional manifold. And as the bias gets stacked on the potential energy landscape, our diffusion sampler will learn to sample another mode as well. So from the result, we get the free energy landscape, as well as we reconstruct the Boltzmann ensemble from the weights that we can calculate from the bias. So when we look at the movie, then we can see that the sample distribution is getting tilted to new modes, and we also get the free energy convergence as a result of this training. So this is like a short introduction of what is happening here. So I'll start from setting up the problem on like sampling in chemistry. So why do we want sampling in chemistry is informally, we're given the energy function and the description of system, as well as the thermodynamic conditions that the system is in. And we want to sample like possible configurations of atoms in the configurational space given the system. So if we want to sample like 6 water molecules in certain conditions, then the result might be like different possible cluster configurations of water that we have. And for the LPS structure, we might want to sample different polymorphs of the solar system given the composition that we have. So this is formalized as a sampling from the Boltzmann distribution. So ideally, we want to generate independent, and identically distributed samples from the distribution that is given as an exponential of negative reduced energy function. And this reduced energy function encodes the system as well as the thermodynamic conditions that the system is in. And depending on the ensemble that we want, we would have a different form of this reduced energy function. So for example, if we have a canonical ensemble, then the reduced energy function would be minus beta, which is the inverse temperature parameter times the energy of the system. And if we want a grand canonical ensemble with possibly different number of particles, then we will get a tilted version of this energy function with the chemical potential of that particle. So people have been training training a mole to sample the chemical configurations, basically using 2 different main ingredients. So first way is to learn from available data that is sampled by existing methods like molecular dynamics or Monte Carlo simulations. And in this case, we can leverage like maximum likelihood or 4KL-based training of the sampler mole. And alternative way is to learn from the energy. So given that we don't have the data sample a priori, but we have some kind of energy function that describes a system, we want to train like a sampler mole from the feedback from the energy function that we have. And historically, this has been started from the very seminal work of Boltzmann generators, which use normalizing flows from like the prior distribution and transport it into data distribution so that we can either train it by the maximum likelihood from data like the data samples, or by using reverse scale with energy functions. And normalizing flows provide exact likelihood evaluation so that it enables such training, but it's the normalizing flow models are sometimes less expressive than like the later generation of generative models, like diffusion models. So there has been two major paradigms in terms of like sampling model perspective, where people try to make normalizing flows more capable by developing more scalable architectures or training schemes. Or alternatively, people have been leveraging diffusion samplers, which I'll introduce today, which is basically training diffusion models by energy functions. So if we think of diffusion samplers, the motivation is that it's similar to diffusion models that is trained by the data points. So we want to control the stochastic differential equation or diffusion models by using the reward tilted distribution that is given by the multiplication of the base density of the diffusion process and the exponential of the reward function that encodes like what is a good structure or a good sample that we want to tilt the distribution to. And the target is we basically, if this is the FDE that defines the base generated process, we want to learn a control term that tilts the final distribution according to this reward. And when we want to sample from the energy function to identify this reward tilted distribution as a Boltzmann distribution, then the reward function that we have to use here is the negative energy function, and the additional term that defines the initial base density that we get from the base generated process. There are like several different ways to realize this kind of training by energy scheme in the context of diffusion samplers. And one that I'll be using today is called like adjoint sampling, which uses the reciprocal adjoint matching objective. And informally introducing, it is similar to score matching in database generative models, but it is now supervised by the energy function feedback instead of data points. So if we think of score matching, then we will start from a prior distribution, and we have a prior sample as well as the data sample that is randomly selected from the available data points that we have. And we, like, according to this diffusion process, like we will sample, like add noise to the data point to generate like a possible noise structure during the diffusion process. And we will match the score, like the intermediate control, using the difference between the prior sample and the final data sample. So we are kind of pushing the intermediate data points to the direction that is getting close to the data points, so that eventually when we follow the control vector field that is learned during training, then we will stochastically get closer to the data points that we already have. And so this is what we can do when we have data points available. And the joint matching is kind of similar. So we start from a prior distribution, and we also have a final distribution. But now the target distribution is defined by the energy function instead of data points. So how do we do this? Is we start from a prior sample, and we follow the current control using the diffusion process. Then it'll get to some structure or some data point on this potential energy landscape. And then we can evaluate the potential energy, like the negative gradient of energy, which is essentially the force. And force will direct us to, like, force encodes the information of this potential energy landscape, where, like, in which direction that we have to propagate to get to lower energy states in this energy landscape. So informally, if we project this kind of force direction to the intermediate control and stochastically optimize this control to follow the direction of force, then when we follow the learned diffusion process, then we will, like, the diffusion process will guide us to lower energy regions of the potential energy landscape. So that is kind of informal version of adjoint sampling. And practically, given that, so in order to use this reciprocal adjoint matching objective, we have a condition that the prior distribution and the data distribution has to be independent in the base process. So the easiest case is that we have like a degenerate prior that is a delta function that is centered at 0. And given that process, we can match the intermediate control vector fields against the scaled version of energy gradient that is that contains the energy function as well as the initial like base distribution density at the final time step. And yeah, we can match the control to that kind of transform energy gradient for the noise version of the final data point that we get from current control. And when we repeat this kind of matching process during training, then we're guaranteed to get the correct Boltzmann distribution after the training. So this kind of training scheme has been applied to examples like amortized conformer generations, where we have some kind of training samples of the molecules, and we do the reciprocal adjoint matching for the training samples using the previous training objective. And after the training process, we have some kind of conformer generation model that is trained by energy function instead of the actual conformer samples that we have. And we can use this model as like a chemically transferable version of conformer generator as well. So this effectively works as a diffusion model that is trained on energy instead of data samples. And this has been extended to adjoint Schrödinger bridge sampler, which tries to solve the problem that for adjoint sampling objective, we need independent prior and target distribution. But if we have some kind of corrector model that corrects the effect of non-independent prior and target sample, like prior and target distributions, and that we can effectively use the similar training scheme with this kind of additional corrector term that is learned by another matching objective, as shown here, like using the score of the base distribution process. And I wouldn't go into too much detail, but now ASDS allows us to use some kind of so that this realizes similar setting to previous diffusion models or flow models where we can use like arbitrary prior and target distribution and train a generating model that maps like the arbitrary prior to target distribution. And like these kind of diffusion samplers works well in low dimensional examples, but practically when we want to apply this to chemical systems, then our dimensionality of samples would be really high. For example, if you look at the alanine dipeptides, which is like a smallest practical benchmark of actual molecular conformer generation examples, we have 22 atoms in alanine dipeptide, which correspond to 66 dimensional sampling space. And in this high dimensional sampling case, we always get some kind of mode-seeking behavior. When we look at the training objective of diffusion samplers, then how we get the feedback from energy function is we use the current version of parameters and follow the diffusion paths and get the samples. And we get signal using that sample and push it towards the lower energy parts of the potential energy landscape. So basically, if we if we initially land in like a specific mode, then we will always get signal that pushes us to the lower energy part in that mode. And when we want to explore different modes, then we have to rely on the noise that is added according to the base distribution process. So if potential energy landscape is quite complex and high dimensional, then the exploration of new regions are based on pure luck. So it is not guaranteed. And practically, if we look at the samples generated from the adjoint Schrödinger bridge sampler, then you can see that for like more populated modes, it gets the correct behavior that reproduces the ground truth distribution. But for less populated modes, it's really hard to learn those. And ASBS and other diffusion samplers sometimes misses those modes. And in terms of like chemical sampling, when we want to characterize different modes or like different configurations that chemical systems can have, then missing modes are kind of critical, and we will want to fix this kind of problem. And so basically, we want to get out of the negative feedback loop where we're getting feedback from energy using the samples that we generated. This is quite intense if like we go into like condensed phases. So for example, when we try to sample like liquid or solid system in the condensed phase with periodic boundaries, then if we apply diffusion samplers to liquid systems where system doesn't have like a very large energy barrier, then it kind of works. But when we apply this to solid phases, then we know that there are like lots of like amorphous configurations that have very small like basins that has higher energy than the actual crystalline minima that we might want to sample. But the energy landscape is now too rugged. So if we start from like pure noise and randomly try to explore different modes in the system, then it will very likely get into one of these glassy states, and it'd be really hard to get to the crystalline minima, so that we kind of get like a very different distribution of generated samples versus the reference samples in this crystalline minima. So yeah, this kind of illustrates why this kind of mode collapse problem could be quite intense and critical in some cases.
Yeah. In the previous slide, what's the top and the bottom? What's the difference between the two? Or I think
okay, so difference between the plot on the top. So
yeah,
this plot and the bottom one. Yeah.
Yeah, exactly.
Thanks. So this is like a Lennard-Jones system, and Lennard-Jones system will undergo phase transition according to temperature that we sample from. So at higher temperature, so the upper one is higher temperature where system melts and is in liquid phase, and the bottom one is at lower temperature in the solid phase. So if we increase the temperature, then these kind of like smaller basins would be kind of smoothened out. So like it will be easier to transition from one mode to another without much barrier. So that makes sampling easier. Yeah.
So at higher temperature, we don't have that mode seeking problem as much as in lower temperature.
Yeah, that's correct.
Okay, thanks.
Thanks. Yeah, and also I can't see the chat right now. So if you have any questions, then please raise your hand, and
yeah, no
please feel
worries.
free
If
to
there's
go
a
ahead.
question, we'll just tell it.
Thanks. Okay. Another problem that we want to solve here is even if we have a broader mode coverage from the sampler mode, the sampling efficiency can be very bad if we have like a metastable modes with a very large difference in free energy. And if you assume that we have a free energy difference of delta F, then IID sampler will produce like 1 to the exponential of minus beta times delta F sample ratio in these two different regions. And for example, in practical settings, like one of the practical setting of sampler is we want to sample the bound and unbound configuration of protein and ligand. Then we know that the equilibrium constant in this case could go to like nanomolar affinity settings, where if we assume that we have an IID sampler of this protein and ligand system, then the sample number ratio could go up to like 10 to the 9th. So like if we want to sample this like unbound configuration, then it'll be really, IID sampling would be really inefficient way of doing that. And even though like our nature itself is kind of IID sampler, we don't want to do IID sampling in computer because of the gap between what we can simulate and what happens in reality. So less populated regions like unbound configurations are important because like chemical processes like binding or reactions happen in real time. So, and it involves like a very large number of simultaneous microscopic events. So nature explores the full ensemble of like full thermodynamic ensemble that we have, while in simulations, like MD or MCMC would propagate everything in like a very small time steps. And even if we do IID sampling, what we can sample using the mole, like the number of samples that we can get from the mole is much smaller than what happens in reality. So in summarizing, like before going on to the methodology, if we summarize what is the practical requirement for chemical Boltzmann sampling, is the first thing is that we want to do weighted sampling. So it's kind of non-IID sampling where we generate a pair of sample and the weight that is assigned to that sample instead of IID samples. And then we'll use a self-normalized estimator of physical properties where we like gather that physical property of each sample according to the weight that is assigned to the sample to reproduce the Boltzmann average of the physical property. And another consideration is on the accessible component. So let's assume that we are given the atom types or like the topology of molecule given the bonding in that molecule. And one like kind of mainstream example that we encounter while sampling is the isomerism of molecules. So for like any kind of amino acids in a protein, we have two kind of mirror symmetric configurations that we call L amino acid and D amino acid. And we know that like all the in nature, we only have one kind of amino acid because like interconversion between like these two configurations are really slow with very high transition barrier. So there are like different chemical processes with different activation barriers and different time scales that correspond to that barrier. But when we consider kind of sampling problem given the atom types or possibly the topology of molecule, we might only want to sample like one of these kind of isomeric configurations. And this could be like kind of informally defined as we only want an accessible component that is kinetically connected up to some time scales. So in this case, like we don't want to sample all kinds of possible configurations, but we only want to sample the subspace of the configurational space that is configurationally stable up to like practically relevant timescales. So now I will kind of introduce well-tempered ASPS, which is the algorithm that we developed to solve this kind of practical requirements. And we solved this using leveraging the enhanced sampling technique that existed in molecular sampling literature for a while. So Basically, inner sampling is any kind of algorithm that facilitates the efficient sampling over of the rare events that happens in chemical systems by biasing the simulation in some form towards different modes that we're interested in. And there are different flavors of inner sampling. And methods like parallel tampering is something that we could do without too much knowledge of the system. But many inner sampling algorithms leverage something called collective variables, which is a low-dimensional descriptor of a system that encodes which direction is the slow or important motions in the system. So for example, if we look at alanine dipeptide or peptide systems, then we know that the backbone torsion angles are the slowest, the rotation of these torsions are the slowest motion in the system. And for host guest complexes or protein ligand binding, we know that the the distance between the host and guest molecules are the descriptor of the system that describe the slow motion of binding. And if we identify these collective variables, then we can either apply some kind of a harmonic restraint along these collective variables, as in umbrella sampling, or we can adaptively stack up the bias along these low-dimensional coordinates, as in metadynamics. So we kind of fill up the potential energy landscape so that we can get over the barrier. Or similar but alternative way of doing this is we use some kind of averaged force along this coordinate, and we apply the negative average force at each time step, so that we kind of effectively shave off this barrier to get over the barrier, which is exemplified this adaptive biasing force algorithm. And for the current work, we'll leverage a variant of metadynamics called well-tempered metadynamics that is known to have a good convergence behavior. So practically, this is instantiated by stacking up a Gaussian bias along collective variable every few MD steps. So we update the bias on the collective variable space by this amount. And so it's like a multiplication of a Gaussian with stacking up the Gaussian with a height that has some kind of discount factor that is defined by this discount factor gamma. And yeah, this will look like the movie on the right. So as we stack up the Gaussian biases, this kind of barrier will be filled by some kind of, so we can think of this as stacking up a computational send on the tensor energy landscape. And after running this until convergence, the bias that we stack up using Gaussians will converge to some kind of smoothened version of the potential energy mean, potential of mean force. And by potential of mean force, or PMF, by we call here, is actually the negative log marginal density over this collective variable space. So essentially, having this final bias on top of the potential energy landscape that we have means that we will be essentially sampling from a distribution that is smoothened by this factor of gamma, and which means along these low-dimensional coordinates, we will be sampling as if the temperature is gamma times temperature instead of the original temperature. So this kind of discount factor controls how much we want to smoothen out the free energy landscape along the collective variable space. So when we think about the practical requirements for Boltzmann sampling, this is a formalized version of what we had previously. So there are 3 requirements of first of which is having a restrained sampling of that is the kinetically connected component of the configurational space that we're interested in. And for this, we will use some kind of restraint potential that is 0 in regions that we are interested in, but like it penalizes when we go outside. For example, when we look at this kind of isomerization example, and we know that the improper torsion angle centered at this chiral carbon would identify whether we are in this region of phase space or in another one. So we can construct some kind of flat bottom harmonic potential that is zero when we are here, but like that follows the harmonic potential when we go outside. And we can use that kind of restraint to focus the sampling in the region of interest. And for other two requirements, so the second of which is whether we can reconstruct the Boltzmann ensemble from the sampling scheme. And the third one is considering whether we get like efficient sampling over all regions of phase space. We will use the previously introduced well-tempered bias to selectively increase the sampling temperature along the collective variables. So in words, it looks complicated, but essentially this is now a combination of energy-based sampler training plus the enhanced sampling algorithm that I introduced previously. So practically it works in a two like hierarchical training settings. So the inner loop is the diffusion sampler training. And we start from like at each time step during training, we will have some kind of bias that is constructed using the well-tempered bias update. And for that bias, we will train the neural sampler using the original potential energy plus the bias that is stacked on top of the, like on the collective variable space. And we do this while during training while updating the bias in the outer loop. So after training the diffusion sampler, we'll draw like conditionally IID best-of configurations. So we generate molecular configuration at the time step, and we project that to the collective variable space. And we do well-tempered bias update on that position. So essentially, we're kind of realizing this stacking bias mechanism, not using molecular dynamics, but using the diffusion sampler that is getting trained. So the diffusion sampler, yes, please.
No, go ahead, you can finish. I'll ask afterwards.
Okay, yeah. So essentially the diffusion sampler and well-tempered bias update is kind of intercalated to each other so that we, after training, we will get the same converged bias from which we can reconstruct the marginal density of on the collected variable space, as well as from the IID samples that is generated by this diffusion sampler. We can unbias the stack bias by using the Boltzmann weight from the bias to reconstruct the Boltzmann, like original Boltzmann ensemble corresponding to the potential energy landscape that we have. Yes, questions?
Yes. So my question is, if I'm understanding this correctly, is it that so you have the potential energy surface at the beginning, and like the more you have places where you sample, the more you want to fill those holes essentially. And so you correct that energy surface essentially, and you get a different distribution. And so like this enhanced sampling method is based on a molecular dynamic method, and it's not used for molecular dynamics. It's used for effectively like diffusion sampling, but you're basing it off of that method.
Yeah, that's correct. Yeah, that's the
Okay,
exact.
thank you. Just wanted to be sure I understood correctly. Thank you.
Thanks. So now I think it'd be nice to compare like what's the advantage that we gain from combining enhanced sampling with diffusion sampler instead of MD-based sampling algorithms. So the advantage here is that when we combine enhanced sampling with MD, then essentially we have to follow the time correlated sampling algorithm while stacking bias. That means when we use diffusion samplers instead, then we don't have like a time correlated moves. Instead, the sampler will generate IID samples according to the bias that we have. So that means we can kind of parallelize the exploration to different modes in cases where we have like high barriers and there are like many metastable states. So when our chemical systems is kind of complex, then we will get advantage of this kind of like using diffusion samplers instead of time correlated samplers. Practical disadvantages could be where the first thing is that we need more restraint potentials. So we have to be careful in setting the restraint potential, because now that we have diffusion sampling to suggest like the next step samples, when we think of like the chirality inversion, then we don't have to consider the inversion of chirality during MD, because when we follow the physical trajectory, then inverting the chirality is a very high activation barrier move. So it wouldn't happen in MD, but it can happen in diffusion samplers because we explore by adding noise. So there's one practical consideration on setting up the restraint potential. And another one is in MD, like moving from one configuration to another requires one force evaluation. But when we want to generate a new data point from diffusion sampler, then we have to integrate the stochastic differential equation from the prior to sample to target distribution by some number of function evaluations, which is usually like a few hundred function evaluations. So, and this kind of like additional cost has been usually have not been considered in diffusion sampler for like chemical sampling, but it's actually practically important because we want to make an efficient sampling algorithm. So if we combine this kind of algorithm with classical force fields, then it would be always more efficient to move along the energy landscape using MD instead of spending like hundreds of number of function evaluations using SDE. So I'll identify this like disadvantages later, but eventually if we combine the sampling algorithms with something much slower than classical force fields, like machine learning force fields, then we'll see that the diffusion sampler approach could be actually practically advantages, even in terms of off-clock time of sampling. So we'll start from like a very classical example of sampling alanine dipeptide. So we start from, so in like training examples, we will start from some amount of pre-training data. So this is because when we think of the diffusion sampler, then the diffusion process could be either trained by existing samples using score matching, or in this case, we use bridge matching, or like we can leverage energy-based training using adjoint matching. So how do we like leverage the fact that we can train the same mode either using data or using energy is that like up to sampling a single mode without crossing the barrier, then we know that MD is quite efficient because we don't have to integrate like few hundred NFEs, but we can just move on the potential energy landscape. And if we don't cross the barrier, then it would be fairly efficient. So we start from an MD sample pre-training data, and we first train a diffusion sampler, and we turn on the adaptive biasing, the well-tempered bias update mechanism, so that so the dots here are the generated samples, and the color contour represents the bias that has been stacked here. So first we will stack up the bias, and the sample distribution will be tilted to new modes so that now the sampler is exploring new modes. And through the training steps, it'll try to converge to the actual potential of mean force along this collective variable space. And you can see that, like, in terms of the number of energy evaluations that we have, we can actually get quite competitive free energy convergence between two like metastable basins. And when you look at a bit more complex example of alanine tetrapeptides and use like 3 backbone torsional angles as collective variable. And now in this case, we'll also similarly start from the pre-training data that's gathered from a single mode and try to see whether we can we can find all possible 8 metastable state in this collective variable space. And in this case, when we compare to like well-tempered metadynamics, which is the same well-tempered bias update combined with MD versus the bias update mechanism combined with diffusion sampler, and we can see that in terms of number of energy evaluations that we have during training or sampling, we get much faster exploration of states. And this is because when we run MD, then the time-correlated sampling algorithm should explore the modes one by one along the time steps, but the diffusion sampler will stack up the bias in this current mode. And at the same time, it could explore like different directions at once, because every time it will produce like IID samples according to current bias. So practically we get advantage from much faster exploration of different modes. When we look at free energy convergence, then in this case, we can see that both methods get into like lower than chemical accuracy in fairly like short amount of sampling time measured by the number of evaluations, like energy evaluations that we have. And now we will think of like the practical advantages of doing this diffusion sampling, because as we mentioned, this incurs the cost of like integrating the control neural network for few hundred steps. So these kind of comparisons are, so we kind of normalize the sampling time according to number of energy evaluations that we have during sampling. But practically, the energy evaluations here is coming from a classical force field, which is really fast. And majority of time spent on sampling would be coming from the NFVs of diffusion sampler. So now we think of how to make when these diffusion samplers are actually useful. And maybe I'll introduce first the target sampling questions that we have. And one like practical limitations of classical force fields is that we cannot model the bond breaking using classical force fields unless we have like very handcrafted parameterization of bond breaking events. And when we want to sample the reactive energy landscapes, then that means we have to at least use like machine learning force fields or like even quantum mechanical energy evaluations during sampling procedure to correctly describe the energetics of these bone breaking or formation events. And that means, and also like recently, we know that recently, like quantum mechanical calculations have been replaced, like is being replaced by the surrogate energy model called machine learning interatomic potentials, which is basically trained model to reproduce the energies and forces from the quantum mechanical calculations by training on energies and forces labels from those calculations. So this gives like an order of magnitude faster evaluation time than the underlying quantum mechanical calculation, but it's still quite slower than the classical calculations. And for this kind of reactive energy sampling example, we will use the UMA model from her chemistry team, which is trained on like several different chemical spaces of interest, like molecules, materials, and catalysis, molecular crystals, and bulbs. And the team has been generating like a large number of structures with like more than 30 billion atoms, and ran quantum mechanical calculations for those systems and get the energy and forces labels, and trained a single model that can deal with like all kinds of different input tasks according to the task embedding that we have. And so this is like the smallest version of this model has 6.6 active parameters during inference. And this model is much faster than quantum mechanical calculation, but still it is much slower than classical force fields. And now that this is kind of like a the minimal complex or minimal time that we have to spend when we want to sample this kind of reactive energy landscape correctly, then we can do the same thing of like well-tempered diffusion sampler and see whether it gives practical advantage of sampling in terms of actual computation time. So the first example here is like the basic nucleophilic substitution reaction, where we have like one chloride ion coming into this tetrahedral carbon center and another chloride leaving. So we can use these two bond lengths, like forming and like dissociating bond lengths as collective variable. And we can see that we can reproduce the symmetric energy landscape of the transition. And we can also locate the transition state accurately on this collective variable space of distances. And another challenging example is like, so this is like a very simple example because we know exactly how the transition happens. And for these kind of transition states, we can locate the transition states and compute the barrier even without sampling using existing methods like knotted elastic band or other transition state searching algorithms. But this case is where a single transition region leads to two different products. So there's no like single reaction, like reactive channel that connects like a single reactant to single product. So this is the example where we actually need some kind of sampling to identify like or resolve how the transition region looks like. And we can use like the forming bond lengths, so we can use the bond lengths that are being formed as collective variables in this case. And we can resolve the transition region that connects two different products as shown here. And quantitatively, we can see that when we use the well-tempered diffusion sampler, we get correct results compared to the well-tempered metadynamics, which is coupled with MD, so that we know that activation barrier or like other types of features in the free energy landscape is correctly captured using diffusion samplers. But now the important thing is when we look at the time spent on sampling, then, sorry. So if we compare the wall clock time, that is, so if you look at the wall clock time versus the mean absolute error of this free energy landscape that we have, we can see that the like error from like the deviation from the final free energy landscape that we get decreases much faster than when we couple the well-tempered bias update with MD simulations. So it means that we require fewer energy evaluations because diffusion samplers are kind of generating the independent samples on the current energy landscape that we have. And another advantage here is that, so for the identical, like for IID samples that we generated, when we get energy feedback from those samples, we can actually batch energy evaluate for those samples, because now our control like model, as well as the machine learning force field that we use to get energy, are both graph neural networks. So we gain two practical advantages from faster sampling of energy landscape as well as batch evaluation of energies and control mode. And now that we can kind of regard this faster convergence as some form of like effectively distilling a lighter sampler model from like a heavier and universal machine learning potential model. So this is like the main results that we had with the well-tempered diffusion sampler, and I'll now introduce some of the remaining challenges and future directions. One another challenge that we have with enhanced sampling or like enhanced sampling coupled with diffusion sampler is that we have to know what kind of collective variable that we have to use. And for all of the previous examples, we are using simple but like some kind of collective variables that are identified by like human knowledge or like human knowledge of the chemical system. And we can actually get better in terms of this because collective variables are actually could be identified by machine learning algorithms. So for example, if we have like samples from two different metastable states, then we can train some kind of classifier model that predicts whether our current sample is in like one state or another, and use the value from that classifier as a collective variable. So it is commonly referred to as machine learning collective variables in the literature. And we can see that if we couple the well-tempered diffusion sampler with this machine learning collective variables, then we can reproduce the free energy landscape as well as the free energy convergence in a similar way. So this is one way of resolving the problem of like prior knowledge of collective variables. And another possible direction is leveraging, like combining this well-tempered bias update with discrete diffusion samplers instead of continuous diffusion samplers that we had. So for this example, this is like sampling the alloy configurations on FCC lattice. So when we make an alloy of copper and gold, it is known that like we at low temperatures we have like several different alloy configurations like pure copper, pure gold, and copper gold, and like different stoichiometric mixtures. And as we raise the temperature, then they will get disordered. So like copper and gold will like randomly occupy the FCC lattice site. So identifying which modes that we have at certain temperature or like certain thermodynamic condition is also a sampling challenge. And one of my colleagues, Xiao Chengdu, he combined this kind of well-tempered bias update algorithm with discrete diffusion samplers. And at lower temperature, we have like similar problem with either like Grand Canonical Monte Carlo or like Monte Carlo or discrete diffusion sampler of mode collapse, where if we initially have samples from a single mode, then exploring another mode or another configuration is very hard. But by combining the sampling with well-tempered bias update along the concentration coordinate, we can actually stack up the bias and enhance the sampling into different modes as well, so that we can get what is different, like what are the possible orderings of atoms that we have at certain like gold concentration, as well as like what is the free energy difference between configurations. And now when we think of like the remaining limitations of this diffusion sampler, then adding the well-tempered bias update with collective variables means that we're leveraging something that is specific to the system that we are sampling. So unless we have like a transferable model for collective variables or transferable model for bias, then our train sampler is specific to that chemical system. So we can't like amortize over different chemistries, or we can't transfer the current model to different chemistries. But there is like So as we introduce the machine learned collected variables, as well as there's some enhanced sampling algorithms that learns the bias distribution variationally instead of stacking up at the Gaussians. So there are still some hope for systems that share like similar slow degrees of freedom so that we can learn those with machine learning. And second challenge is more broader in terms of like general diffusion sampling. So like the diffusion sampler that is trained by energy has to always compete with alternative method where we leverage the same energy function and just run the classical molecular simulation to obtain data. And we just train diffusion model from data instead of leveraging energy-based training. So as of yet, I think scalable diffusion sampler, like how to train this kind of scalable diffusion sampler is not yet explored, so that currently like the models that are trained from available data are much more practical. But I say like we had MD and MTMC sampling algorithms for like more than 70 years now. So also for the enhanced sampling. So we know like what kind of hyperparameter that we have to choose to get the right data, but we still don't know like what is the recipe for training the scalable version of this. So I think we still have some hope on exploring like what is the correct recipe of training this kind of energy-based sampler at scale. And in terms of that, I'll finalize with like a few considerations for getting into scalable direction. So first thing is kind of similar. So it is pretty clear that we don't want like IID Boltzmann sampler in some cases where we have like different modes with large free energy differences. And in that sense, one way is to leverage like a self-normalized estimator where we have samples with corresponding weights. But another way of doing this is we don't think that much about like different free energies, and we just train a model that can produces like different samples in different modes. So I say like this is some kind of mode exploration task. So it could be beneficial if we separate out the mode exploration task of exploring what modes are possible in the current system versus reconstructing the like correct population in those modes, like using the actual. So the second part being like the exact reproduction of Boltzmann ensemble. And the second challenge here is global versus local sampling. And diffusion samplers can be efficient because it produces identical, so it produces independent sample on the current distribution. But if we think of like the liquid phase or protein in a solvent, then conformational changes in protein is rare event, and it will largely benefit from independent sampling. But for solvent parts, water can, like, unless water is bound in a very specific position, water can diffuse around like without that much barrier. And it means that like so this kind of solvent reorganization could be efficiently sampled just by time correlated samplers. So it might not be worthwhile to like diffuse from the noise to generate independent samples by using several hundred function evaluations. And finally, for like materials or solid systems, and if we want to treat like the material structures in leveraging the continuous samplers, then I think one way to restrict the sampling to crystalline minima instead of like rather than having problem of getting into one of the random glassy state is to use group conditions generating moles. Like when we precondition the network that like the symmetry groups as well as something like Wyckoff positions that particles can go in, then we know that they, like, even in database generative settings, they work better than like unconditional moles. And in energy-based sampler setting, it would be actually much better because we can just efficiently, effectively restrict the sampling energy landscape to where we have like that kind of group conditional landscape. So these are the future directions that I think would be promising for energy-based samplers. So yeah, I'll finalize with acknowledgement. So thanks everyone in fair chemistry team as well as learning matter team at MIT. And yeah, thank you everyone for listening. And I'll take any questions or comments.
No, yeah, just a very quick question. So when you talked about ML methods to learn the collective variables, is it like something that would, for a given system, give you like the collective variables for that system, or like exactly how? Yeah.
Yeah, practically how this works. Yeah, that's a good question. So, so machine learning collective variables usually assume that we like have like a few samples in like from different modes. And so the problem setting is that when we have two or more different modes, then it is actually the challenging part here is that we don't know where is the transition region between those two modes. So, and the local sampling within mode could be efficiently done by MD simulation. So when we have like a sample distribution and different modes, then we can train like a discriminator of those samples that is with target of the mode label. And then the model will learn how to discriminate different modes. And then we take that take that model as a collective variable. So so with that being said, there's slightly a chicken and egg problem of that we have to know where are the modes at the beginning to train this collective variable model. So practically, people start from like a single mode and do enough sampling to identify modes and train a better version of collective variables and iterate this process until we have a good enough collective variable as well as good enough sampling of modes. So yeah, it practically could be more challenging than it looks, but yeah, there has been like lots of method development in this area.
I see, and that doesn't like really address the amortization problem, right? The amortization is something else that you would need to tackle differently, right? Or maybe with an ML method, not exactly, like it's not automatic that this also solves amortization.
That's correct. So amortized collective variable is something that haven't been much explored in MLCV literature. I say if we have like a coherent physical descriptor, like usual descriptor for MLCVs are like bond lengths of specific atoms. So if we think of systems that share like similar features, like if we have like bunch of different tetrapeptides, then we can take the common things like the backbone torsion angles as input features and train a transferable CV. But yeah, it is possible, but it hasn't been explored much yet.
All right, thanks.
Thanks.
Sorry, okay. I have a question on the reactivity. So if I understand correctly, in your case, your collective variable is like the bond length, right, of the different, in that scenario. So you pretty much get that transition state by doing all this sampling, and then you get your highest energy barrier. Is that correct?
Yeah, that's correct.
Okay. So question have you studied like how does it scale with like number of atoms, or like how more complicated it is, the different configurations with respect to like NEVs, which is just a classical way of doing this?
That's also a good question. So, whether like this is scalable versus NEV is, I think, we have to consider like the problem setting here. So, and NEV is a method that identifies like the minimum energy path of transition from one mode to like one energy minima to another. And in this case, we want to reconstruct like the free energy landscape of the reactive system so that we can get like some kind of full energy landscape along like low dimensional coordinates. So in that sense, like, so this is trying to solve like a broader version of the problem that we have. And yeah, so that's like the answer for how do we compare to NEV, like the minimum energy path methods, and whether like these scales with respect to number of atoms in the system is something that is up for exploration. So we have tried like up to, I think currently the largest system with the alanine tetrapeptide, which have like 44 atoms, and we've tried to scale it up to like larger peptide systems, but there's like a problem of like separating out. Sorry, are you speaking?
No, go ahead.
Okay, thanks. So, yeah, for larger systems, like we have a separation of global and local degrees of freedom, and for proteins like signaling, and when we simulate that in implicit solvent, then we actually get a very different behavior from explicit solvent. So, but when we want to do that with explicit solvent, then diffusion process for solvent molecules are kind of inefficient because like solvent reorganization is pretty fast. So yeah, I say this has to be either coupled with like having a better version of like implicit solvent mole or some kind of coarse grain mole, versus like, or alternatively, like devising a way to separate out what is like the slow degrees of freedom or parts that contribute to the slow degrees of freedom that we need to sample with diffusion moles. Does that answers your question?
Yes, thanks.
Thank you.
And there is one question from Luca. In general, how many steps is required to sample with adjoint matching?
Thanks. That's a great question. And for examples that I showed here, I used about 250 steps. And for the amortized conformer generation example, it gives reasonable results in a range of like 64 to 200 function evaluations. So I guess at least we need like probably about 100 or more function evaluations to produce physical examples. And one possible direction to reduce this further is probably using like distillation approaches or flow maps to like jump through the flow or diffusion timestamps. But I think that's currently an active area of research.
Thank you. And then the second part of the question is, are there perspectives for accelerating that with similar approaches to mean flows?
Yeah, I think I already explained the second part. So mean flow is also one way of doing that.
Right, perfect. I think there are no more questions. Thanks a lot, Juno. It was very interesting. We'll put the recording on YouTube and probably send you the link. And yeah, thanks for the great presentation.
Thank you so much.
Thanks everyone for attending.
See you. Have a good day.
You too.